Up to this point in the course, we've been talking about translational motion. That is, we've been talking about the motion of an object along a curved path, which maybe I could draw like this, with this being the x and this being the y axis. The object we were thinking about might be located here, and as time goes by, it moves this way along that path. Well, there's another kind of motion that we need to start talking about now. Let's suppose that instead of traveling along this curved path, we had an object that was following a circular path. It was rotating around some center. You can imagine, for instance, that this is a bicycle tire, and there's a valve stem right here, so that as time goes by, the valve stem rotates from this position around this way, and it ends up over here somewhere. What we want to do in this part of the course is learn how to describe this kind of rotational motion. That is, we want to do kinematics on it. And then we want to look at why things rotate the way they do. So we want to do some mechanics on it. We're going to develop this second part of the course in an exactly parallel way to what we did the first part when we talked about translational motion. Where we started was with a set of definitions for kinematic quantities: position, velocity, and acceleration. We'll do the same thing here. Then we looked at some constant acceleration motion. We'll do that again. And then we moved into mechanics, and we talked about forces and energy and momentum. Here we'll do all of those same things, looking at the analogous rotational quantities. Let me start by reminding you of some of our translational kinematic definitions. Once we defined the position of an object, which was this guy here, the next thing we defined was displacement, which was delta r, the final position minus the initial position. If I drew that on this plot, maybe the object started here and it ended up over here, so that the displacement vector would look like this, the change in position. Then we defined two velocities. We defined the average velocity, which was the displacement divided by the time, delta r over delta t, and we defined the instantaneous velocity, the time derivative of the position vector. And you remember that the velocity vector tells you two things. It tells you how fast and in what direction the object is moving. After that, we defined two accelerations: average acceleration, which was change in velocity over change in time, and instantaneous acceleration, which was the time derivative of the velocity vector. Also, the second time derivative of the position vector. The acceleration vector also told us two things. It told us whether the object was changing speed or changing direction. Both of those things are tied into the acceleration. If the velocity vector changes, speeds up or slows down, or turns, you have an acceleration. Now we want to do the same kind of thing and write down some kinematic expressions or kinematic definitions for rotational motion. We can imagine, first of all, taking these exact definitions and applying them to this rotational case. We could set an xy coordinate system and measure the position of this valve stem as x and y and see how it changes, take its derivatives, and do all of this, and that would certainly work. The trouble is that when you have objects that are rotating, a Cartesian xy coordinate system is inconvenient. There are lots of sines and cosines that show up. I'm not going to show you all these, but you can imagine that R would have sines and cosines in it to account for the x and y components, and all these derivatives are going to have sines and cosines in them. So it turns out to be kind of messy. It would work, but it's not the easiest way. The much better option is to define a new set of kinematic quantities that have this rotational sense built into them. So we're going to define three new quantities. Instead of position, velocity, and acceleration, we're going to define angular position, angular velocity and angular acceleration and build into their meanings this natural rotational motion. I'm going to write a table up here. When we used to talk about position r, now we're going to talk about angular position, which we'll call theta. When we used to talk about velocity v, now we're going to talk about angular velocity, omega. When we used to talk about acceleration a, now we're going to talk about angular acceleration, alpha. These things on the right tell us the same thing as these guys, just in a rotational sense. Position located the object for us. That's what the angular position is going to do. It's going to tell us where it is in its rotation. The velocity told us how fast and in what direction something was translating. The angular velocity omega is going to tell us how fast and in what direction something is rotating. The acceleration a told us if an object was speeding up, slowing down, or turning. The angular acceleration alpha is going to tell us whether the object is spinning faster or slower, or whether it's changing its axis of rotation. Same quantities, different meanings. The meanings are in a rotational sense now. So let's draw some pictures, write these definitions down, and start to get a feel for them. The first thing we need to do is to define the angular position, the rotational analog of this. And that's going to be the angle theta. So let's assume that our object is right here. That's our angle theta. But we need this to be a vector. We need a direction on this thing also. The direction of angular quantities is given by the right-hand rule. If we consider this to be our 0, what you do to find the direction of this angle theta, I'm going to write it as a vector here, is to put your right hand fingers along the reference direction right here. So your right hand fingers should be pointing to the right, and you curl your fingers towards the object. So you curl your fingers this way. And what should happen when you do that is that your thumb should point out of the screen towards you. That is the direction of this angle theta. It doesn't mean the object is coming towards you. What it means is that the object is rotating around your thumb. The object is curling in the same sense that your right hand fingers do around your thumb. So that's the direction of this angle theta. If the valve stem is at this spot at some initial time, and then it moves over here at some final time, we could call this theta I, and we could call this theta F, and we can define the angular displacement. Delta theta, which is a vector, is theta F minus theta I. The angular displacement in this case would look like this. That angle right there is delta theta, the angular displacement. That's its magnitude. Its direction is again going to be found by the right-hand rule. Put your right-hand fingers along the reference, that's the initial location, curl them towards the final, and your right-hand thumb should point out of the screen towards you. That would be the direction of this angular displacement. Angular displacement tells you the angle you've rotated through and the direction you've rotated in. It's completely analogous to this guy over here, how far and in what direction your position changed. Now the next things to define are the rotational analogs of these velocities. We have two of them. We have average angular velocity and we have instantaneous angular velocity. We define them in exactly the same way. We attach the same meaning to them, just with a rotational sense. It's displacement over time for the average quantity. So it's angular displacement over the time for the average. And in the instantaneous version, we shrink delta t down to 0, and the delta becomes a derivative. So we get d theta dt. This thing tells us how fast and in what direction the object is rotating. The faster it's spinning, the larger the magnitude of this, and the direction of it tells us whether it's going clockwise or counterclockwise. A quick word on convention. Over here in translational motion, our usual convention is to take x positive this way and y positive up. In rotational motion, our usual convention is to consider rotations to be positive when they're counterclockwise, when they're going this way. So we tend to call those positive rotations, and if an object is going in the clockwise direction, we would call that a negative rotation. So the sign convention that we typically attach to rotational motion is positive counterclockwise, measured from the positive x-axis. So omega tells you how fast and in what direction you're rotating. Now for the acceleration quantities. There are again two. There's an average angular acceleration, and there's an instantaneous angular acceleration. Let's write down the definitions. They are exactly the same as over here, just with the rotational variables and the rotational meaning along with it. The average angular acceleration is the change in the angular velocity divided by the change in time. And the instantaneous angular acceleration, as delta t shrinks to 0, those deltas become the derivative, and we get the time derivative of the angular velocity, which is the second time derivative of the angular position. So there are the kinematic definitions for our rotational variables: angular position, angular velocity, and angular acceleration. They mean the same thing as our translational variables, just with rotational interpretations attached to them. Now let me show you one more thing before we leave this first talk on rotational motion. I want to redraw this circle that's rotating so that we can talk about the units. Let's suppose that we have this wheel that's going to be rotating. I'm going to draw it again here. And it has some radius r. The valve stem maybe starts here, and it's going to rotate over to here. I want us to think about the path traced out by this valve stem and think of the length of the arc that it sweeps out. Let me draw that in red. So as the valve stem goes from here to here, it's going to sweep out this circular arc. I'm going to make it thick here so we can see it. And that arc, following the circle, is going to have a length of s. Imagine we take a piece of string and we lay it on this curved path, and then we straighten it out. It would have a length of s. Now there is a relation among that arc length s, the circle's radius r, and the angle theta subtended by that arc. The arc length s equals r times the angle theta. This is the arc length formula, and it is the foundation that we use to define our unit of angle theta in SI units. What is the angle theta? It's the ratio of two things: the arc length s divided by the radius r. Notice what the units are. In SI units, s would have units of meters. It's how long this red piece of string would be. And r would also be in units of meters. It's the radius of the circle. So theta has units of meters per meter. And the meters cancel, and there's really no units. This is a dimensionless quantity. But we like to give some name to this unit, even though there really isn't anything there. We call it a radian. The ratio of the arc length to the radius is what we call a radian. So our SI unit of angle is the radian. Notice that 1 radian occurs where the arc length equals the radius. If I laid a string out here on the radius and then laid it along this curve, the angle subtended by that would be 1 radian. And it turns out to be about 57 degrees. But we can find the exact conversion among degrees and radians a slightly different way. Suppose I want to go once around this whole circle, and I want to see how many radians are in one revolution. Well, if I go once around the whole circle, and I have one revolution here, the arc length going once around is the whole circumference. That's 2 pi r. And I divide that by r, so I get 2 pi radians. In one revolution, in once around a circle, there are 2 pi radians, and of course there are 360 degrees. So this is the conversion factor we can use. One revolution is 2 pi radians, and that is 360 degrees. All right, let me stop there, and in the next talk we'll introduce a few more kinematic quantities for rotational motion. We'll talk about the kinematic equations, and in the meantime we'll look at some problems using these definitions right here.